Welcome to part 2 of our tutorial on diode circuits. Okay, so in this tutorial we shall discuss pretty much about the bridge rectifier as promised in the end of tutorial 1. Okay, so here we have the bridge rectifier circuit, as you can see here. Okay, that's it. So in case of the bridge rectifier circuit, you'll see that it's pretty much an improvement over the full wave rectifier. Should shortly come to the improvements. And now, in order to draw the bridge rectifier circuit, we have, as that happened before, we have a step down transformer in the beginning connected to the AC mains supply. Okay, so here goes the primary coil connected to the AC mains, and here's the secondary coil of the transformer connected across a diode bridge. Okay, so what's a diode bridge? A diode bridge pretty much looks like somewhat like this. Okay, having a problem with drawing, it's been pathetic since childhood. Okay, so pretty much don't mind about that. So let's just concentrate on the diode circuit. Okay, so here we have the diode bridge, as I said before, and the AC input is applied across these two terminals, as you can see here. Now these two terminals, let me just name them as the terminals A and terminals B. Okay, and here the terminals of this transformer secondary coil, I just named them as 1 and 2. Okay, the other two terminals that we have here, C and D, okay, which is obtain our output from that terminal. Okay, so here goes the terminal D, and here from we have the terminal C, and across these two we have our load resistance connected, across which we shall obtain our output voltage. Okay, so there it goes. So this is the circuit of a bridge rectifier. All right, so now what it does is that the bridge rectifier performs in a little different way than that in case of the full wave rectifier, but the output of the bridge rectifier is pretty much looks like the same as that in case of the full wave rectifier. So if we just draw the output graphs, so before that we just let's just assume that we have an input AC signal to our bridge rectifier circuit like this. Okay, so this is an input sinusoidal signal, okay, with a peak value of Vm. Okay, so based on that, whenever we have the positive peak of, or rather the positive half cycle of this input signal arriving across the terminals 1 and 2 of the transformer secondary, we get an output, or rather we see that the terminal 1 becomes forward biased, or rather becomes goes to the positive voltage levels, and the terminal 2 to the negative voltage levels, as this whole signals are available over here. So based on that, we have the terminal A, or rather the node A, at a positive voltage and node B at a negative voltage, and that causes a diode. Okay, let me just name them first. This is D1, D2, D3 and D4. Okay, so coming back to a discussion again, so when we have the positive voltage at the terminals 1 of the transformer and a negative voltage at terminal 2, we have the same, we have this positive voltage falling on node A, which causes diode D2 to be forward biased, since it's available on its, since the diode D2 has a positive voltage on its anode, and now at terminals B the negative voltage falls, and therefore diode D3, having a negative voltage on its cathode, becomes forward biased again and begins to conduct. So during this half cycle we have a current flowing through the diode D2 and through the load resistance back through the path to node C, and then through the diode D3, and finally back to the terminal 2 of the transformer. Okay, so now it generates an output voltage of the polarity that looks somewhat like this, since this is the direction of the current flow. Okay, so now in case of the second half cycle, let me just show you what happens. Okay, so this was the voltage polarity across the first half cycle. Okay, and the second half cycle, what happens is that we have let me just rub it out, the case of the first half cycle. Okay, that's it. Now in case of the second half cycle, as I said, that the polarity reverses Okay, so now the terminal 1 has a negative voltage compared to terminal 2, and since for AC the polarity reverses, we can see here that the second half cycle enters into the negative voltage region. So that's why terminal 1 has a negative voltage compared to terminal 2. So at point A, or rather at node A, we have a negative voltage that forward biases diode D1, since a negative voltage is available on diode D1's cathode, and in case of the terminal B, we have the same positive voltage of that across terminal 2 appearing, so which forward biases the diode D4 as it has a positive voltage on its anode, and therefore during this half cycle the diode D4 conducts and the current flows through RL as before, and we have a similar voltage polarity output developing across the load resistance. And now this current goes back through to the node C, and then now it goes through diode D1 since it's forward biased, and finally into the terminal 1 of the transformer secondary. Okay, so having said that, we can see here in both the cycles we have the same voltage polarity developing. So now since the output voltage just keeps varying pretty much the same way as that of the input half cycles, so if we just draw the output curve, then we'll get something like this. Here the output across the rectifier is somewhat like this. If we just take a closer look, it's of just the same type as that obtained in case of the full wave rectifier, as I said before. So now since the output voltage across the bridge rectifier circuit varies in the direct proportion to the input half cycles of the AC input voltage, so they just resemble the input half cycles of the AC voltage, but contrary to that, there is no change of polarity as I showed here. Okay, so all the half cycles are of the same polarity in case of the output across a bridge rectifier. So this output, as you can see here, keeps on varying with time, okay, sometimes increasing and decreasing. So this is termed as a pulsating DC output. Okay, so for a rectifier that converts AC into DC, we need an output that would be a straight line without varying with time. So now this output, as we can see here, varies with time in a far greater way. So now these components that we have here that just keeps on varying with time, all these heads that you can see here, these time variant components are referred to as ripples, okay, on the output voltage. So now we just need to smoothen out the ripples so that we can get a output voltage that looks pretty much a straight line, okay, as in case of a proper DC. So for that reason, in order to process the output into a proper DC signal, we shall use a filter capacitor instead. Okay, so here's our filter capacitor named as C. Okay, there goes filter capacitor. Okay, so now this filter capacitor, what it does is it just smoothens out the output waveform, and it quickly discharges during the first half of the arrival of the first half cycle, and then it just charges quickly and then discharges slowly, and this process just goes on. And if we draw the output across the filter capacitor, then it would look somewhat like this, or let me just name it VOF. Okay, so here goes the divisions for the half cycles. Okay, now the output across the filter capacitor would look somewhat like this. Capacitor would charge quickly during the first half of the input half cycle, and then discharge slowly, and then charge again and discharge slowly, charge again, discharge slowly, and so on. So here we can see that although we don't obtain a straight DC voltage, okay, over here, which is a straight line of course, but still we are able to get somewhat close to it, as the variation of the output voltage is somewhat reduced a bit. So it's more or less a straight line, or rather close to a straight line. And now these minute variations that we can see here won't be perceivable, but it helps in increasing the output voltage, or rather reducing the ripples to a great extent. So we just obtain, or rather just use this kind of approach. Okay, without this kind of approach, in order to smoothen out or just filter out the ripples, okay, and generate a voltage output across the bridge rectifier circuit that resembles somewhat close to a DC, or rather a proper DC output. So now the filter capacitor, whenever we use it in the circuit, so this falls into the class of filters. So if you all want to know a detail about filter circuits, then kindly refer to a tutorial about filters, or rather filter circuits used in rectifiers. Okay, so now let me just say one more thing, that this filter capacitor, whenever it's added, there should be another resistance added across it. Now the value of this resistance should be in the kilo ohms range, or rather should always be of the order of about 10 k ohm. Okay, so here this is referred to as the bleeder resistance. Okay, now its order should be about the 10 k ohm. Okay, so not less than that, so otherwise this won't provide a proper regulation. So the use of the bleeder resistance is for two purposes. One is to provide a proper percentage regulation. Okay, percentage regulation. Okay, so greater the regulation factor, better is our rectifier circuit. And number two is that discharge of the capacitor during switch off. Okay, discharging capacitor during switch off. Okay, so whenever the circuit, or rather a rectifier circuit, is just switched off and it's not working, all the charge stored in the capacitor is just filtered out, or rather is just drained out by the bleeder resistance. Okay, so that helps to filter out the residual charges in case of that stored in the filter capacitor, and thereby increases its life as there is no overloading of the capacitor. So that way the bleeder resistance just helps us. So having said that, just let's move on to the mathematical parameters obtained in case of a bridge rectifier circuit. So the output DC value or expression is the same as that of the full wave rectifier, which is 2 Vm by pi, where Vm is the peak input voltage of the input AC voltage. Okay, so there it is. The peak inverse voltage in case of this bridge rectifier is of course the input AC voltage across the reverse bias diodes. So for each half cycle we have two diodes conducting, and for the two we have two diodes reverse biased. So for each half cycle we have this peak voltage appearing across the terminals 1 and 2 of the transformer secondary. So for each half cycle the reverse bias diodes experience the peak input voltage of the AC. So this VI that's available across the transformer secondary is just nothing but the peak value of the input AC voltage. Okay, that's the peak inverse voltage across each diode during the non-conducting phase, or whenever they're just reverse biased. Apart from that, we have the transformer utilization factor of this circuit, that is 0.812, which means that the circuit is able to convert, or rather rectify, about 81.2% of the total amount of input AC signal available to it across the transformer secondary. So this circuit, as we can see here, the bridge rectifier circuit, is pretty much more efficient than the full wave rectifier. As I said before, it's the improvement over the full wave rectifier circuit. So having a peak inverse voltage of Vm, and that it falls across two diodes, so it basically just the two diodes they distribute this peak inverse voltage, and that's why the lifetime across each diode increases. So other than that, since it has a TUF of about 81.2%, so that means that it can be used in case of applications where high voltage and current are required. So based on these conclusions, we just say that the bridge rectifier is much more efficient than the full wave rectifier, and is of course used in a greater deal in case of all the industrial application of power supplies and such others. So with that, we come to the end of our tutorial about the diode bridge rectifier. So hope it's been helpful to you, and see you next time in our next tutorial. So till then, it's goodbye and thank you.